So this problem says a piece of metal weighing 59.047 grams was heated to 100 degrees Celsius and then put into 100 milliliters of water, which was initially at 23.7 degrees Celsius. The metal and the water were allowed to come to an equilibrium temperature, which was determined to be 27.8 degrees Celsius. Assuming no heat was lost to the environment, calculate the specific heat of the metal. Okay, so this is our typical calorimetry problem. Calorimetry. So we don't know the specific heat of some substance, and so we take it and we drop that substance after heating it up into water, and then we measure the temperature change of the water. We know the specific heat of water, so we can then use this information to calculate, kind of backwards, the specific heat of our unknown object, which is oftentimes a metal. So for these problems, what I like to do is make myself a little table, because we have a lot of pieces of information here and we need a way to organize them. So in my calorimetry table, I keep track of my M, my C, my T final, and my T initial, which will then allow me to calculate my delta T. And I do this for both the water and for the metal. And so I write all this information out in this table format, and then once I find the value of Q for the water, I know that my Q of the metal will be the same value, just with the opposite sign, as whatever heat is absorbed by the water will be released by my metal. So let's start organizing our information. A piece of metal weighing 59.047 grams. So that's the mass of my metal, 59.047 grams. Was heated to 100 degrees Celsius. So that's my initial temperature of the metal. We heated it up to that. It started there. My initial temperature of my metal is 100 degrees Celsius. And then put into 100 milliliters of water. Okay, so there's no volume of water here, but we know that for water, 1 milliliter is the same as saying 1 gram. So if we have 100 milliliters of water, we also have 100 grams of water. Okay, so that's the mass of my water. The water was initially at 23.7 degrees Celsius. So that's my T initial, 23.7 degrees Celsius. The metal and water were allowed to come to an equilibrium temperature. And this will always happen. Whenever you drop something into water and the thing cools off and the water heats up a little bit, the temperature that the two items end at, the water and whatever you're putting in the water, will be the same, because heat will be released by whatever you're cooling off and absorbed by the water until the temperature of the two are the same. So they will always come to an equilibrium temperature, meaning the temperature that they're at where they're no longer transferring heat. So that equilibrium temperature in this scenario was determined to be 27.8 degrees Celsius. So that's the final temperature both for the water and for the metal, 27.8 degrees Celsius. It's for both of them. Okay, and now that we have our final and initial temperature for both, we can calculate our delta T for each of these items, the water and the metal. So I'm going to do 27.8 minus 23.7. Oops, I didn't type that in right. 23.7. And that gives me a change of 4.1 degrees Celsius. And now I'm going to do 27.8 minus 100, which gives me a temperature change of negative 72.2 degrees Celsius. Negative 72.2 degrees Celsius. Okay, so now I know I'm going to be calculating Q for each of these, and I don't have either of my values for specific heat. I don't have them given in the problem, but I do know one of them because I know water has a specific heat of 4.184 joules per gram degrees Celsius. You have to remember to plug in that piece of information here. You always know the specific heat of water, so don't forget to use it when you have a problem like this. Now I have everything I need to calculate the amount of heat that was absorbed by the water. So I'm going to put Q of the water equals 100 grams times C, which is 4.184 joules per gram degrees Celsius, times delta T, which is 4.1 degrees Celsius. Okay, so I'm going to substitute this into my calculator. Let's see, 100 times 4.184 times 4.1, which gives me 1715.44. And that's equal to the Q of the water. Now I just need to figure out my units. Grams are going to cancel because I have 1 in the numerator, 1 in the denominator. Degrees Celsius is the same way, so my units are just joules, which makes sense. That is a unit of heat energy. Okay, so now that I know the Q of the water, I know that the Q of the metal is going to be the negative version of the Q of the water. If the heat energy is absorbed by the water, then that means it's released by the metal. So my Q of my water equals the negative Q of the metal. So that makes the Q of my metal equal to negative 1715.44 joules. Notice I'm not rounding this value because this is an intermediate value, meaning it's not my final answer. So let's substitute this in. This time we're going to be solving for C of our metal. Okay. So we have negative 1715.44 joules equals M, so 59.047 grams, times C of the metal, which we don't know, times our delta T, which is negative 72.2 degrees Celsius. Okay, so I'm actually going to go ahead and combine these like terms before I move them to the other side. So I'm going to do, let's see, clear, negative 72.2 times 59.047. So I have negative 4263.1934 times the C of the metal equals negative 1715.44. I'm going to leave off my units now that I'm doing my algebra. I know my final units for specific heat are going to be joules per gram degrees Celsius. So I'm just going to leave them off while I do my algebra. I'm going to divide by negative 4263.1934 on both sides. It's a lot of writing here. So these cancel. And my C of my metal is going to equal whatever this answer is. Now, pay attention to your negatives. What I notice here is that I have a negative on top and bottom, so when I divide this out, my answer should come out being a positive number, because a negative divided by negative is a positive. If you do get a negative number for specific heat, know that you have definitely done something wrong. Specific heat should always be a positive number. You will never get a negative value here. So I'm going to do, go up and select my previous answer, and I need to add a negative in front of it, divided by this answer here, and that gives me 0.40238. Okay, now I just need to look at my significant figures. Back up in my problem, I have 1, 2, 3, 4, 5, 4, 4, 3, and 3 significant figures. So my least number of sig figs will be 3. So coming back down here, 1, 2, 3 significant figures. So I'm going to round my final answer. The C of the metal is equal to 0.40, and then this 3 is going to make the 2 stay at 2. And then my units are joules per gram degrees Celsius. And there is my final answer right there.